Metabolic adaptation to climate and distribution of the raccoon, Procyon lotor, and other Procyonidae. John N. Mungus, John Seidensticker, and Kathleen P. Malky Johnson. Introduction. Defining the problem. Procynid origins. The major carnivore radiations took place about 40 million years before present, MYBP, in the late Eocene and early Oligocene. Ewer 1973, page 363, Wayne et al. 1989. Between 30 and 40 million years before present, a progenitor split into the Ursid and Procynid lineages, which evolved into present-day bears, pandas, and raccoons, Wayne et al. 1989. The taxonomic relatedness of pandas to bears and raccoons has been tested extensively, and a number of authors have summarized current thinking on the problem. Martin, 1989, Wayne et al., 1989, Wozencraft, 1989a, 1989b, Decker and Wozencraft, 1991. Davis, 1964, pages 322 to 327, and others. Leon and Wines, 1956, Todd and Pressman, 1968, Sarek, 1976, O'Brien et al., 1985. Place the giant panda, Ailuropoda melanoluca, with the ursids. The taxonomic status of the red panda, Ailurus fulgens, appears to be less certain. Some current investigations align the red panda with bears. Segal, 1943, Todd and Pressman, 1968, Hunt, 1974, Ginsberg, 1982, Wozencraft, 1984, page 56 to 110, 1989a, whereas others place them intermediate to procynids and bears. Worster and Bernishke, 1968, Sarek, 1976, O'Brien et al., 1985, or in close relationship to the giant panda. Tegel et al., 1986. The procynid radiation took place in North America and produced forms that were mostly arboreal and omnivorous. Eisenberg, 1981, page 122. Martin, 1989. The center of this diversification occurred in Middle America. Baskin, 1982, Webb, 1985b. During the Miocene, Darlington, 1963, page 367, Webb, 1985b. Fossil procynids from the late Miocene are represented in Florida, California, Texas, Nebraska, Kansas, and South Dakota. Baskin, 1982, Martin, 1989, and includes such genera as Basariscus arctanasua, Sionasua, Paranasua, Nasua, and Procyon. Baskin, 1982, Webb, 1985b. During the Miocene, procynids underwent a modest radiation within tropical and subtropical climates of North America's central and middle latitudes. Sionasua, which has close affinities to Arctanasua, Baskin, 1982, appears in tropical South America in the late Miocene and immigrated there either by rafting across the Bolivar Trough or by island hopping through the Antilles archipelagos. Marshall et al., 1982, Marshall, 1988. Thus, procynids were found on both continents prior to formation of the Panamanian land bridge. Darlington, 1963, page 367, 395. Marshall et al., 1982. Marshall, 1988. Origins of Basariscion and Potos are obscure, but probably occurred in tropical rainforests of Middle America. Baskin, 1982, Webb, 1985b. A subsequent Pleistocene dispersal carried several modern genera, Table 1, across the Panamanian land bridge into South America, Webb, 1985b. Basariscus and Basariscion, the most primitive genera in Procyonidae and Potocinae subfamilies, respectively. Table 1, Wozencraft, 1989a, Decker and Wozencraft, 1991. In the early Tertiary, mid-latitudes of North America were much warmer than they are now, but not fully tropical, and temperate deciduous forests associated with strongly seasonal climates occurred only in the far north. Barghorn, 1953, Colbert, 1953, Darlington, 1963, page 589, 590. Major climatic deteriorations with their attendant cooling of northern continents occurred during the Eoligocene transition, in the middle Miocene, at the end of the Miocene, and at about 3 million years before present late Pliocene. This last deterioration corresponds with closure of the Panamanian Isthmus. Berggren, 1982, Webb, 1985a. Climatic deterioration went on at an accelerating rate during the late Tertiary, with glacial conditions developing at the poles by the mid-Pliocene. Barghorn, 1953. Therefore, throughout the Tertiary, as continents cooled, northern climate zones moved toward the tropics. Barghorn, 1953, Colbert, 1953, Darlington, 1963, page 589, 590, 594, 595. Webb, 1985a. Table 1. Classification of recent Procyon after Wozencraft 1989a and Decker and Wozencraft 1991. Information in parenthesis indicates general geographic distribution, modified from Kortluck and Ramirez, Pulido 1982, and Pauglayan, Newell 1975. SA equals South America, CA equals Central America, M equals Mexico, US equals United States, C equals Canada. Lowercase letters preceding geographic areas signify north, south, and west. Order Carnivora Bowditch, 1821. Suborder Caniformia Kretsoi, 1945. Family Procyonidae Gray, 1825. Subfamily Potocinae Trossart, 1904. Genus Potos E. Jeffrey and G. Cuvier, 1795. P. flavus, South America, Central America, Mexico. Genus Bassaricion Allen, 1876. B. alani, South America. B. bedardi, South America. B. gabii, Northern South America, Central America. B. lasius, Central America. B. pauli, Central America. Subfamily Procyoninae Gray, 1825. Genus Bassaricus coes, 1887. B. astutus, Mexico, Western United States. B. sumicrasti, Central America, Mexico. Genus Nasua Stor, 1780. N. narica, Northern South America, Central America, Mexico, Southwest U.S., United States. N. nasua, South America, Southern Central America. Genus Nasuella Hollister, 1915. N. olivacea, South America. Genus Procyon Stor, 1780. P. cancrivorus, South America, Southern Central America. P. gloveraleni, Barbados. P. insularis, Maria Madre Island, Maria Magdalene Island. P. Lotor, Central America, Mexico, United States, and Southern Canada. P. maynardi, Bahamas, New Providence Island. P. minor, Guadalupe Island. P. pygmaeus, Mexico, Quintana Roo, Cozumel Island. Footnote A. The several named forms of Bassaricion are a single species, Bassaricion gabii, Wozencraft, 1989a. Footnote B. These are considered conspecific in some current taxonomies, Courtluck and Ramirez-Pulido, 1982. However, the scheme followed here maintains them as separate species, Decker, 1991. Footnote C. Several named forms of Procyon are a single species, Procyon Lotor. Wozencraft, 1989a. During the late Miocene, late Pliocene, and Pleistocene, the Bering Land Bridge between North America and Asia formed periodically, offering an avenue for dispersal between northern continents. Darlington, 1963, page 366, Webb, 1985a. However, by the late Tertiary, northern continents had cooled to the extent that climate, with its attendant sharply defined vegetative zones, became the major factor limiting dispersal by this route. Darlington, 1963, page 366, Webb, 1985a. Those Holarctic mammals that did cross the Bering Land Bridge in the late Tertiary were cold-adapted species associated with relatively cool but not alpine climates. Darlington, 1963, page 366, Ewer, 1973, page 369. Among carnivores, this included some canids, ursids, mustelids, and felids. Darlington, 1963, pages 393 to 395. 397. Webb, 1985a. Proconids, however, did not cross the Bering Land Bridge into Asia, and Ewer, 1973, page 369, ascribes this to their being an essentially tropical group. Miocene radiation of proconids occurred at a time when two of the four major climatic deteriorations, Middle and Late Miocene, were taking place, Webb, 1985a, 1985b. These deteriorations had the effect of cooling the middle latitudes to the extent that temperate forest forms began to appear in mid-latitude floras, along with a rapid influx of herbaceous plants. Raccoon, 1953. The proconid radiation did not penetrate beyond these climatically changing middle latitudes, which implies that these animals were warm-adapted, and were, therefore, physiologically excluded from reaching the Bering Land Bridge. Today, 3 of the 6 genera and over half of the 18 species that comprise Proconidae, Table 1, Wozencraft, 1989b, remain confined to tropical regions of North and South America. Hall and Kelson, 1959, pages 878 to 897. Poglet and Newell, 1975, Courtluck and Ramirez-Pulido, 1982, Nowak and Paradiso, 1983, pages 977 to 985. Typical proconids. McNabb, 1988a, contends that basal metabolism is a highly plastic character in evolution, and he has amply shown that ecologically uniform species are more apt to share common metabolic rates than taxonomically allied species from drastically different environments. McNabb, 1984a, 1986a, 1986b, 1988a. Proconids represent a taxonomically allied group that shared a common ecological situation for millions of years. Consequently, members of this family might be expected to show some uniformity in their HB. Basal and thermoregulatory metabolism of several proconids have been measured. Ginkgo, Potus flavus, Mueller and Kulzer, 1977, McNabb, 1978a, Mueller and Roast, 1983. Coatis, Nasua, Cheviera Hugo et al., 1980, Mugas et al. In preparation, and Nasua Naruka, Scholander et al., 1950, C. Mugas et al. In preparation. Ringtail, Basiriscus astutus, Chevalier, 1985, and crab-eating raccoon, Procyon cancrivorus, Scholander et al., 1950c. In general, these species have HBs that are 40 to 80% of the values predicted for them by the Kleiber, 1961, page 206 equation. Lower than predicted HB is viewed as an energy-saving adaptation for prosonids living in relatively stable tropical climates. Müller and Kulzer, 1977. Chevirang, Hugo et al., 1980. Müller and Rost, 1983. This implies that lower than predicted HB is a general prosonid condition and that it represents a characteristic that evolved in response to the family's long association with tropical and subtropical forest environments. The atypical prosonid. Although most prosonids are found in only tropical to subtropical climates, the North American raccoon, Procyon Lotor, Figure 1, has a much broader distribution that extends from tropical Panama, 8 degrees north, to southern Canada. In Alberta, Canada, its range reaches the edge of the Hudsonian life zone at 60 degrees north. For distribution maps, see Hall and Kelson, 1959, pages 878 to 897, and Pogley and Newell, 1975. Range extensions and an increase in numbers have been noted in Canada and in parts of the United States since the 19th century. Lotz and Anderson, 1979, Kaufman, 1982, Nowak and Paradiso, 1983, pages 977 to 985. Thus, Procyon Lotor is more complex ecologically than other prosonids, particularly when one takes into account its highly generalized food habits. Hamilton, 1936, Stewart, 1943, Staines, 1956, pages 39 to 51, Greenwood, 1981. And the wide range of habitat types, forest, prairie, desert, mountain, coastal marsh, freshwater marsh, and climates, tropical to north temperate, in which it is successful. Whitney and Underwood, 1952, page 1. Hall and Kelson, 1959, page 885. Lotz and Anderson, 1979. Kaufman, 1982. On this basis, it is clear that Procyon Lotor has deviated from the typical prosonid portrait and has become the consummate generalist of the Prosonidae. The hypothesis. Our general hypothesis was that whereas most contemporary prosonids have retained the metabolic characteristics of their warm-adapted ancestors, Procyon Lotor possesses a different set of adaptations, which either evolved as characteristics unique to this species or were acquired from its ancestral stock. In either case, its unique adaptations have given Procyon Lotor the physiological flexibility to generalize its use of habitats and climates and expand its geographic distribution to a much greater extent than other prosonids. Hypothesis testing. We tested our hypothesis by comparing Procyon Lotor with several other prosonids, Bassaricus astutus, Nasua nasua, Nasua naurica, Procyon cancrivorus, and Potos flavus, on the basis of their 1. Basal metabolic rate, HB, 2. Minimum wet thermal conductance, CMW, 3. Diversity of diet, DD, 4. Intrinsic rate of natural increase, Rmax, and, when data were available, 5. Capacity for evaporative cooling, EC. In genetic sense, each one of these variables is a complex adaptive characteristic, expression of which is determined by the interaction of several genes. Prosser, 1986, pages 110 to 165. Experience has shown that a given species will express each one of these variables in a specific manner that is relevant to its mass, physiology, behavior, and environmental circumstance. Thus, different expressions of these variables may represent specific climatic adaptations. Prosser, 1986, page 16, that have been selected for by evolutionary process. Because these variables are interrelated with respect to regulation of body temperature and energy balance, they have co-evolved in each species to form an adaptive unit. For each species, measured and calculated values for the first 4 variables were converted into dimensionless numbers and used to derive a composite score that represented its adaptive unit. Climatic distributions of these species were then compared relative to their composite scores. Adaptive significance of the variables. Basal metabolic rate and intrinsic rate of natural increase. Basal metabolic rate represents the minimum energy required by an animal to maintain basic homeostasis. Lusk, 1917, page 141. Kleiber, 1932, 1961, page 251. Benedict, 1938. Brody, 1945, page 59. Robbins, 1983, page 105 to 111. For mammals, basal metabolic rate appears to be determined by complex interactions between their body size. Kleiber, 1932, 1961, page 206. Benedict, 1938. Brody, 1945, pages 368 to 374. Hemmingson, 1960, pages 15 to 36. McNabb, 1983b. Calder, 1987. The Climate in Which They Live. Scholander et al., 1950c. McNabb and Morrison, 1963. Holbert and Dawson, 1974. Skolnick and Schmidt-Nelson, 1976. McNabb, 1979a. Vogel, 1980. Their Food Habits. McNabb, 1978a, 1978b, 1980a, 1983a, 1984a, 1986a, 1986b, 1988a, 1989. And their Circadian Period. Ashoff and Pohl, 1970. Prothero, 1984. Some species have higher mass-specific basal metabolic rate than others, and this variation appears to be tied to ecological circumstances rather than taxonomic affinities. McNabb, 1988a, 1989. Basal metabolic rate is important ecologically because it serves as a measure of a species' minimum obligatory energy requirement, and under many circumstances it represents the largest energy demand associated with a daily energy budget. King, 1974, pages 38 to 55. McNabb, 1980a. Mugas and King, 1981, pages 37 through 40. Recently, it also has been implicated as a permissive factor with respect to intrinsic rate of natural increase of mammals. Henman, 1983, Lilgraven et al., 1987, Nichol and Thompson, 1987, Thompson, 1987, via its direct effect on their rates of development and fecundity. McNabb, 1980a, 1983a, 1986b. Henneman, 1983, Schmitz and Levine, 1984, Glazier, 1985a, 1985b. The implication of this latter point is that those species with higher basal metabolic rates also have faster rates of development and greater fecundity and hence enjoy the competitive advantage of a higher intrinsic rate of natural increase. Basal metabolism is therefore a highly plastic character in the course of evolution. McNabb, 1988a, page 25, that has a profound influence on each species' life history. Minimum thermal conductance. Whole body resistance to passive heat transfer is equal to tissue resistance plus coat resistance. Within limit, these resistances can be altered. Tissue resistance can be varied by changes in blood flow, whereas coat resistance can be changed by piloerection, molt, and behavior. When whole body resistance is maximized, maximum tissue and coat resistances, passive heat transfer is minimized. The inverse of resistance is conductance. Therefore, maximum whole body resistance is the inverse of minimum thermal conductance. Right. Minimum thermal conductance, CM. Minimum thermal conductance is readily derived from metabolic chamber data, and it is commonly used to describe an animal's capacity to minimize passive heat transfer. Minimum thermal conductance interacts with basal metabolic rate and body mass to set the maximum temperature differential a mammal can maintain without increasing its basal level of heat production. The low temperature in this differential is the lower critical temperature, TLC. Mass-specific minimum thermal conductance for mammals is negatively correlated with body mass. McNabb and Morrison, 1963. Herod and Kessel, 1967. McNabb, 1970, 1979b. Bradley and Devers, 1980. Ashoff, 1981. And for any given mass, its magnitude is 52% higher during the active rather than the inactive phase of the daily cycle. Ashoff, 1981. However, some mammals have minimum thermal conductances that are higher or lower than would be predicted for them on the basis of body mass and circadian phase. Seasonal variation in minimal thermal conductance, higher values during summer than winter, has been reported for many northern mammals that experience large annual variations in air temperature. Scholander et al., 1950a, Irving et al., 1955, Hart, 1956, 1957. Irving, 1972, page 165. Some tropical mammals with very thin fur coats and others with nearly hairless bodies have high minimum thermal conductances, McNabb, 1984a, as do burrowing mammals, McNabb, 1966, 1979b, 1984a, and the kit fox, Vulpes macrotis. Golightly and Omart, 1983. Some small mammals with low basal metabolic rates tend to have lower than predicted minimum thermal conductances. Small marsupials, McNabb, 1978a. Heteromid rodents, McNabb, 1979a. Several anteaters, McNabb, 1984a. The Arctic hare, Lepus arcticus, Wang et al., 1973. The ringtail, Basiriscus astutus, Chevalier, 1985, and the fennec, Phenicus zerda, Noel Banholzer, 1979. Thus, in spite of its mass dependence, minimum thermal conductance also has been modified during the course of evolution by selective factors in the environment and by the animal's own metabolic characteristics. Capacity for evaporative cooling. Latent heat loss occurs as a result of evaporation from the respiratory tract and through the skin, and except under conditions of heat stress, it is a liability in thermal and osmotic homeostasis. Calder and King, 1974, page 302. Evaporative cooling, defined as the ratio of evaporative heat lost to metabolic heat produced, can be used to quantify thermoregulatory effectiveness of evaporative cooling and to make comparisons of heat tolerance between species. Thermoregulatory effectiveness of latent heat loss is not just a function of the rate of evaporative water loss, but also of the rate of metabolic heat production. Lasitsky and Seymour, 1972. For example, a low metabolic rate minimizes endogenous heat load and thus conserves water, whereas the opposite is true of high metabolic rates. Lasitsky and Seymour, 1972. Some mammals that live in arid regions have evolved low metabolic rates and thus capitalize on this relationship to reduce their thermoregulatory water requirement. McNabb and Morrison, 1963, McNabb, 1966, Macmillan and Lee, 1970, Noel Banholzer, 1979. What is evident, therefore, is that an animal's capacity for increasing latent heat loss must evolve together with its basal metabolic rate and minimum thermal conductance in response to specific environmental demands. Diet, McNabb, 1986a, 1988a, 1989, demonstrated that for mammals, departures of basal metabolic rate from the Kleber, 1961, page 206 norm are highly correlated with diet and independent of phylogenetic relationships. McNabb's analysis indicates that for mammals that feed on invertebrates, those species with body mass less than 100 grams have basal metabolic rates that are equal to or greater than values predicted by the Kleber equation, whereas those with body mass greater than 100 grams have metabolic rates that are lower than predicted. Grazers, vertebrate eaters, nut eaters, and terrestrial frugivores also have basal metabolic rates that are equal to or greater than predicted, whereas insectivorous bats, arboreal folivores, arboreal frugivores, and terrestrial folivores all have rates that are lower than predicted. McNabb, 1986a, found animals with mixed diets harder to categorize, but in general he predicted that their basal metabolic rates would be related to 1. A food item that is constantly available throughout the year, 2. A food item that is most available during the worst conditions of the year, or 3. A mix of foods available during the worst time of the year. Although these correlations do not establish cause and effect between food habits and basal metabolic rate, McNabb's analysis does make it clear that the relationship between these variables has very real consequences for an animal's physiology, ecology, and evolution. Experimental design and summary. In this investigation, we measured basal and thermoregulatory metabolism, evaporative water loss, and body temperature of raccoons from north-central Virginia. Measurements were conducted on both sexes in summer and winter to determine how season and sex influence these variables. We then compared the data for this widely distributed generalist with data from literature for its ecologically more restricted relatives. Dietary data for all species were taken from literature, as were reproductive data for calculation of intrinsic rate of natural increase. Our analysis demonstrated clear differences between Procyon lotor and other proconids with respect to basal metabolic rate, minimum wet thermal conductance, diversity of diet, and intrinsic rate of natural increase. The composite score calculated from these variables for Procyon lotor was much higher than those derived for other species, and there was a positive correlation between the number of climates a species occupies and the magnitude of its composite score. Data on evaporative water loss, although not complete for all species, suggested that tropical and subtropical proconids have less capacity for evaporative cooling than Procyon lotor or Bassaricus astutus. It was clear, therefore, that with respect to its thermal physiology, Procyon lotor differed markedly from other proconids, and we contend that these differences have allowed this species to become a highly successful climate generalist and to expand its distribution into many different habitats and climates. Our analysis also suggested that the cornerstone of Procyon lotor's success as a climate generalist is its basal metabolic rate, which is higher than the proconid norm. Acknowledgements. The authors would like to thank John Eisenberg and Devra Kleiman for their support and encouragement throughout the study. This investigation was supported by research grants from the West Virginia School of Osteopathic Medicine and Friends of the National Zoo. Logistic support was provided by the National Zoological Parks Conservation and Research Center and the Departments of Mammalogy and Zoological Research. Our ability to conduct physiological research at the CRC was made possible by the thoughtful support and encouragement provided by Chris Wemmer. His excellent staff at CRC, especially Jack Williams, Jr. Allison, and Red McDaniel, were very helpful in providing hospitality and logistical support to the senior author and his family during their various visits to the center. The assistance of several people at the National Zoo also is gratefully acknowledged. Mitch Bush and Lindsay Phillips not only provided veterinary support throughout the investigation, but also performed surgical procedures required to implant temperature-sensitive radio transmitters in several raccoons. Olav Ofdale made his laboratory available to us at various times and loaned us equipment to use at CRC. Miles Roberts and his staff provided care for our captive raccoons in the Department of Zoological Research during various parts of the investigation. Greg Sanders and Ken Halama, supported by FONZ assistantships cared for our captive raccoons at CRC, provided assistance in the laboratory whenever needed, and were an invaluable source of aid. Their friendship and help is gratefully acknowledged. Ellen Brody and Andy Meyer, supported by WVSOM and a student work-study grant, respectively, provided assistance in the laboratory. David Brown, John Eisenberg, Mary Etta Height, Brian McNabb, Steve Thompson, and W. Chris Wozencraft critically reviewed various phases of the manuscript and provided many helpful suggestions. We deeply appreciate the work of Jean B. McConville, whose beneficial editorial suggestions helped us improve several early versions of the manuscript. We also gratefully acknowledge Diane M. Tyler, our editor at the Smithsonian Institution Press, whose expertise helped us mold the manuscript into its final form. Jill Mellon and Sriyani Mithalapa, supported by FONZ traineeships, assisted in measuring the daily cycle of body temperature in raccoons. The Virginia Commission of Game and Inland Fisheries gave us permission to use wild-caught raccoons in this project. Materials and methods. Live trapping. Raccoons were caught from May 1980 through December 1984 on a trapping grid of 30 to 35 stations, 1 or 2 live traps per station, that covered about 1/3 of the National Zoological Park's Conservation and Research Center, CRC, near Front Royal, Virginia. Seidensticker et al., 1988. Hallett et al., 1991. Animals were trapped during 10 consecutive days each month, and in this 5-year interval, 407 raccoons were captured and marked with tattoos and ear tags. All captured animals were individualized with respect to age, reproductive status, physical condition, parasite load, and mass and body dimensions. These data characterized the structure and dynamics of the raccoon population at CRC and provided information on the annual cycle of fattening for raccoons in north-central Virginia. Animals used for metabolic measurements were captured at CRC about 1.5 kilometers south of the trapping grid and thus were genetically representative of the area. 6 males were captured and measured during the summer of 1983. These animals were kept isolated for a week before being measured and were released later that summer at the site of their capture. The other 7 animals used in our study were from the collection of the National Zoological Park, and all of them had their origins at CRC. Metabolic studies. Basal and thermoregulatory metabolism. Metabolic measurements conducted at CRC were carried out on 8 males during July and August 1983, on 4 females and 3 males from November 1983 through March 1984, and on 4 females during June and July 1984. Raccoons were housed throughout the study such that they were constantly exposed to a natural cycle of temperature and photoperiod. Weather records for the Front Royal area indicate that average temperatures are around -0.5 degrees Celsius in January and 23.3 degrees Celsius in July. Crockett, 1972. Light to dark, L to D, periods for the latitude of CRC, 48 degrees 55 clicks north, United States Department of the Interior Geological Survey, 1972, calculated from duration of daylight tables, list 1971, pages 506 through 512, were 14.9 to 9.1 and 9.4 to 14.6 hours light to dark for summer and winter solstices, respectively, and 12.2 to 11.8 hours for light to dark for vernal and autumnal equinoxes. Our animals were fed a measured amount of food daily, and they usually ate most of what was provided. Occasionally, these animals would eat very little or none of their ration, and on some days they would eat all that was given to them. We fed them either feline diet, ground horse meat, or canned mackerel, star-kissed, along with high-protein dog chow, Purina. When available, fresh fruit also was added to their diet. Water was always provided ad libitum. Footnote 1. The use of product brand names in this publication is not intended as an endorsement of the products by the Smithsonian Institution. Measurements were conducted during the raccoon's daily inactive period, sunrise to sunset, in both summer and winter. Oxygen consumption was measured in a flow-through metabolism chamber at 5 degrees Celsius intervals from -10 degrees Celsius to 35 degrees Celsius. Animals were held at each temperature until the lowest rate of oxygen consumption had been obtained and maintained for at least 15 minutes. During each determination, oxygen consumption was monitored for 30 minutes to 1 hour beyond a suspected minimum value to see if an even lower reading could be obtained. Raccoons attained minimum levels of oxygen consumption more quickly at warm, over 10 degrees Celsius, than at cold temperatures. Depending on the temperature, therefore, each measurement took from 2 to 5 hours to complete. On days when 2 measurements could be completed, the second trial was always at a temperature 10 degrees Celsius warmer than the first. The metabolism chamber was constructed from galvanized sheet metal, 77.5 by 45.5 by 51 centimeters, equaling 180 liters, and was painted black inside. Within the chamber, the animal was held in a cage, 71 by 39 by 33 centimeters, constructed from turkey wire that also was painted black. This cage prevented the raccoons from coming into contact with the walls of the chamber, yet it was large enough to allow them to stand and freely move about. The bottom of the cage was 11 centimeters above the chamber floor, which was covered to a depth of 1 centimeter with mineral oil to trap urine and feces. During measurements, the metabolism chamber was placed in a controlled temperature cabinet, modified Montgomery Ward Model 8969 freezer. Air temperature, TA, in the metabolism chamber was regulated with a Yellow Springs Instrument Model 74 temperature controller. Air temperature was controlled to plus or minus 1 degree Celsius at temperatures below freezing and to plus or minus 0.5 degrees Celsius at temperatures above freezing. The chamber air and wall temperatures were recorded continuously. Linsys Model LS64 recorder during each experiment, and except during temperature changes, they were always within 0.5 degrees Celsius of each other. Columns of diorite and ascarite removed water vapor and carbon dioxide, respectively, from air entering and leaving the chamber. Dry carbon dioxide-free room air was pumped into the chamber. Gilman Model 13152 pressure vacuum pump at a rate of 3 liters per minute. Gilmont Model K3203 20 flow meter. Downstream from the chemical absorbents, an aliquot 0.1 liter per minute of dry carbon dioxide-free air was drawn off the chamber exhaust line and analyzed for oxygen content. Applied Electrochemistry Model S3A Oxygen Analyzer, Model 22M Analysis Cell, and Model R1 Flow Control. All gas values were corrected to standard temperature and pressure for dry gas. Oxygen consumption was calculated from the difference in oxygen content between inlet and outlet air using Equation 8 of Depicus and Hart, 1957. Each raccoon was fasted for at least 12 hours before oxygen consumption measurements began. At the start and end of each metabolic trial, the animal was weighed to the nearest 10 grams. Doctor's Infant Scale, Detecto Scales Incorporated, Brooklyn, New York, USA. The body mass used in calculating minimum oxygen consumption and evaporative water loss was estimated from timed extrapolations of the difference between starting and ending weights and the time at which these variables were measured. Evaporative water loss. During metabolic measurements at temperatures above freezing, evaporative water loss was determined gravimetrically. Upstream from the chemical columns, an aliquot of air, 0.1 liter per minute, was drawn off the exhaust line and diverted for a timed interval through a series of pre-weighed 0.1 milligram U-tubes containing diorite. The aliquot then passed through a second series of U-tubes containing ascarite before entering the oxygen analysis system. Evaporative water loss was calculated using Equation 1. E equals parentheses MW times point V subscript E parentheses over parentheses point V subscript A times T times M parentheses, where E is evaporative water loss, mg times g superscript minus 1 times h superscript minus 1. I suppose that's to the power of minus 1? Yeah, okay, so where E is evaporative water loss, mg times g to the power of minus 1 times h to the power of minus 1. mw is mass of water collected, mg. Point V subscript E is rate of airflow into the chamber, 3 liters per minute. Point VA is the rate of airflow through the U-tubes, 0.1 liter per minute. T is length of the timed interval, h, and m is the estimated mass of the raccoon at the time of sampling, g. Body temperature. Veterinarians at the National Zoological Park surgically implanted calibrated temperature-sensitive radio transmitters, Telonics Incorporated, Mesa, Arizona, USA, into abdominal cavities of 2 female and 2 male raccoons. Transmitter pulse periods were monitored with a digital processor, Telonics TDP2, coupled to a receiver, Telonics TR2 164/166. During some metabolic measurements, body temperatures of these animals were recorded to the nearest 0.1 degrees Celsius at 30-minute intervals. The daily cycle of body temperature of these raccoons also was measured once a month. Calibrations. Calorimeter. At the conclusion of these experiments, the accuracy of our calorimetry apparatus was tested by burning an ethanol lamp in the metabolism chamber. During these tests, a carbon dioxide analyzer was incorporated into the system, Beckman LB2. Results demonstrated that we measured 84% of the oxygen consumed by the lamp as well as 84% of the water and carbon dioxide it produced. Standard deviation equals plus or minus 2.6, plus or minus 5.5, plus or minus 5, and plus or minus 3.6, respectively. N equals 27. Average respiratory quotient, RQ, calculated from these data was that's a typo? That's a typo. Was 0.657 plus or minus, what is going on here? Average respiratory quotient, RQ, calculated from these data was 0.657 plus or minus 0.008, N equals 27, which is 99.5% of that predicted, 0.66. McNabb, 1988b, reports that the accuracy of open-flow indirect kilometry systems, such as ours, depends on the rate of airflow through the animal chamber. If flow rates are too low, there is inadequate mixing of air within the chamber, and the rate of oxygen consumption, as calculated from the difference in oxygen content of air flowing into and out of the chamber, Depicus and Hart, 1957, is underestimated. At some critical rate of airflow, which is unique to each combination of chamber and animal, this situation changes such that measured rates of oxygen consumption become independent of any further increase in flow rate. McNabb, 1988b. In recent tests of our system, where we burned the ethanol lamp at a variety of chamber flow rates, the efficiency of measurement increased linearly as flow rate increased, and the critical rate of airflow was about 6.7 liters per minute. This appeared to explain why a flow rate of 3 liters per minute underestimated oxygen consumption of the ethanol lamp. Our earlier tests of the efficiency of our system indicated that although we underestimated actual oxygen consumption of the ethanol lamp, we did so with a fair degree of precision, probably because flow rates were closely controlled. During our metabolic measurements, chamber flow rates also were closely controlled at 3 liters per minute, and we believe, therefore, that these measurements also were carried out with a high degree of precision. Consequently, all measured values of oxygen consumption and water production were considered to be 84% of their actual value and were adjusted to 100% before being included in this report. Body temperature transmitters. The calibration of all temperature-sensitive radio transmitters drifted over time. Transmitters were calibrated before they were surgically implanted and again after they were removed from the animals. Although the drift of each transmitter was unique, it was also linear. S. Tomkiewicz, Telonics Incorporated, Personal Communication. All body temperature measurements were corrected from timed extrapolations of the difference between starting and ending calibrations. Statistical methods. Values of oxygen consumption, evaporative water loss, and body temperature were plotted as a function of chamber air temperature. Linear regressions of oxygen consumption at temperatures below the thermoneutral zone, Tn, and evaporative water loss at temperatures above freezing were determined with the SAS 1982 GLM procedure. Lower critical temperature, TLC, was determined graphically from intersection of the line representing basal metabolic rate and the regression line representing oxygen consumption below the thermoneutral zone. Slopes and intercepts of regression lines, as well as other mean values, were compared with t-tests. Statistical Analysis System 1982, Ott 1984, pages 138 through 175. Unless indicated otherwise, data are expressed as mean plus or minus standard deviation, SD. Estimating intrinsic rate of natural increase. We employed the method first described by Cole, 1954, to calculate intrinsic rate of natural increase. L equals E to the power of negative R max plus B times E to the power of negative R max A minus B times E to the power of negative R max N plus 1. Equation 2. Why do they do this to us? Where A is potential age of females first producing young, B is potential annual birth rate of female young, and N is potential age of females producing their final young. After life history data were substituted into equation 2, intrinsic rate of natural increase was determined by trial and error substitution. Henneman, 1983. Because intrinsic rate of natural increase represents the genetically fixed, physiologically determined maximum possible rate of increase, data on earliest possible age of female reproduction, highest possible birth rate of female young, and longest possible female reproductive lifespan were used for A, B, and N, respectively. Calculated values, therefore, represent physiological possible, not ecologically possible, intrinsic rates of increase. Henneman, 1983, 1984. Hayson, 1984. McNabb, 1984b. Values of N were derived from longevity records for captive animals, and as these were all large values of similar duration, 14 to 16 years, they had very little effect on natural rate of increase. All species considered have 1 litter per year, and because their sex ratios at birth are about 50-50, variation in B was due to differences in litter size. Therefore, age of first reproduction and litter size had the greatest effect on intrinsic rate of increase, natural increase. Intrinsic rate of increase scales to body mass, Fenchel, 1974, and we remove this effect by comparing each calculated intrinsic rate of natural increase with the value expected, R max E, on the basis of body mass. Henneman, 1983. Comparison of adaptive units. Dimensionless numbers for each of the 4 variables used in calculating composite scores were derived as follows. Ratios of measured to predicted values were used for basal metabolism, HBr, and minimum wet thermal conductance, CMWR. Thermoregulatory ability at low temperatures is closely related to the ratio HBr over CMWR, McNabb, 1966. This ratio was used, therefore, to gauge each species' cold tolerance. For diversity of diet, we use the ratio of food categories actually used by a species to the total number of food categories taken by all species tested, DDR. The ratio of calculated to expected intrinsic rates of natural increase was used to derive Rmax-R. Composite scores were calculated as composite score equals bracket parentheses HBr over CMWR parentheses plus DDR plus R max R bracket over 3, equation 3. The correlation between number of climates these species occupy and their composite scores was tested by linear regression. Results. Body mass. According to monthly live trapping records, the body mass of free-ranging female raccoons increased from 3.6 plus or minus 0.6 kilograms during summer to 5.6 plus or minus 0.8 kilograms in early winter, and the mass of free-ranging males increased from 4 plus or minus 0.5 to 6.7 plus or minus 0.9 kilograms during the same interval. These seasonal changes in body mass were due to fluctuations in the amount of body fat and represent a mechanism for storing energy during fall for use in winter. In summer, captive and trapped male and captive female raccoons had the same body mass, 4.73 plus or minus 0.61, 4.41 plus or minus 0.7, and 4.67 plus or minus 0.88 kilograms, respectively, Table 2. Mass of captive females did not change between seasons, whereas captive males were heavier in winter than summer. P less than 0.005, Table 2. This seasonal change in mass of our captive males was of a much smaller magnitude, 0.6 kilograms, than that observed for wild males, 2.7 kilograms. During winter, captive males, 5.34 plus or minus 1.39 kilograms, were heavier than captive females, 4.49 plus or minus 0.98 kilograms, P less than 0.005, Table 2. Thus, our captive animals maintain a body mass throughout the year that was intermediate to the range of values found for wild raccoons in the same area. Table 2. Body mass in kilograms and basal metabolism. Milliliters oxygen times kilograms to the power of negative 0.75 times H minus to the power of negative 1 of Procyon Lotor in summer and winter. SD equals standard deviation and N equals number of observations. Basal metabolic rate. Within thermoneutrality, basal metabolic rate, ML, milliliters oxygen times G to the power of negative 1 times H to the power of negative 1 was 0.54 plus or minus 0.09 for trapped males in summer, 0.46 plus or minus 0.07 for captive males in summer, 0.42 plus or minus 0.07 for captive females in summer, 0.47 plus or minus 0.06 for captive males in winter, and 0.46 plus or minus 0.1 for captive females in winter, figures 2 and 3. Ratios of these measured values to those predicted by Kleiber, 1932, 1961, page 206, equation are 1.28, 1.12, 1.02, 1.17, and 1.09, respectively. To minimize the effect of body size, Mellon, 1963, and to facilitate comparisons between sexes and seasons and between captive and trapped animals, basal metabolism also was calculated as a function of metabolic body size. Milliliters oxygen times kilograms to the negative power 0.75 times H minus 1, table 2. Based on this analysis, trapped summer males had a higher basal metabolism than captive males, P less than 0.025, or females, P less than 0.005 in either season, table 2. There was no difference in basal metabolism between captive males and females in either summer or winter, and there was no seasonal difference in their basal metabolic rates, table 2. Minimum thermal conductance. Minimum wet and dry thermal conductances were calculated using equations 4 and 5. Equation 4. Minimum wet thermal conductance equals HR divided by TB minus TA. Equation 5. Minimum thermal conductance equals HR minus EEQ divided by TB minus TA, where minimum wet thermal conductance is wet and CMD is dry conductance. Okay, yeah, so I got dry thermal conductance is dry conductance. Milliliters oxygen times G to the power of minus 1 times H to the power of minus 1 times degrees Celsius to the power of minus 1. HR is the lowest resting metabolic rate measured at each temperature. Milliliters oxygen times G to the power of minus 1, negative, yeah, okay, times H to the power of negative 1. EEQ is oxygen equivalent for heat lost by evaporation. EEQ equals milliliters oxygen times G to the power of negative 1 times H to the power of negative 1 equals E times triangle divided by Y, where E is evaporative water loss, mg times G to the power of negative 1 times H to the power of negative 1. Triangle is heat of vaporization for water, 2.43 joules divided by milligrams, and Y is heat equivalent for oxygen, 20.097 joules per milliliter. TB is body temperature, degrees Celsius, and TA is chamber air temperature, degrees Celsius. Only data from animals equipped with temperature-sensitive radio transmitters were used for these calculations. Table 3. Minimum wet and dry thermal conductances. Milliliters oxygen times G to the negative power 1 times H to the negative power of 1 times degrees Celsius to the negative power 1 of Procyon Lotor in summer and winter. Means of values were calculated from equations 3 and 4, SD equals standard deviation, and N equals number of observations. Not reading the table. Figure 2. Relationship between oxygen consumption and chamber air temperature for raccoons in summer. Captive females, open circles. Captive males, closed circles. Trapped males, open squares. Sloping lines represent regressions of oxygen consumption on chamber air temperature, and horizontal lines, basal metabolism. Figure 3. Relationship between oxygen consumption and chamber air temperature for raccoons in winter. Captive females, open circles. Captive males, closed circles. Solid sloping line represents regression of oxygen consumption on chamber air temperature for males and females, and the horizontal line, basal metabolism, for males and females. Minimum wet thermal conductance was calculated for each season from metabolic measurements made at all air temperatures below lower critical temperature, Table 3. Because evaporative water loss was not measured at temperatures below freezing, minimum dry thermal conductance was calculated only from metabolic determinations made at air temperatures between lower critical temperature and 0 degrees Celsius. There was no difference between males and females in summer for either minimum wet thermal conductance or minimum dry thermal conductance. Milliliters oxygen to the power of minus 1 times h to the power of minus 1 times Celsius to the power of minus 1. Data for each sex were combined to give a summer average of 0.0256 plus or minus 0.00284 for minimum wet thermal conductance and 0.0246 plus or minus 0.0019 for minimum dry thermal conductance. Table 3. These summer conductances were 49% higher, P less than 0.005, than those calculated for winter females, 0.0172 plus or minus 0.0023 and 0.0161 plus or minus 0.0027 for minimum wet thermal conductance and minimum dry thermal conductances, respectively. Table 3. Minimum wet thermal conductance and minimum dry thermal conductance were not different from each other in either summer or winter, which indicated that in both seasons, evaporative water loss contributed very little to heat dissipation at temperatures below the thermal neutral zone. Comparisons of thermal conductances calculated on the basis of metabolic body size, Mellon 1963, gave the same results. Evaporative water loss. Evaporative water loss increased as chamber temperature increased in both summer and winter, figures 4 and 5. In summer, the pattern of increase was different for females and males. Polynomial regressions for trapped and captive males produced equations that describe a concave relationship between air temperature and evaporative water loss, whereas the equation for females described a sigmoid curve, table 4, figure 4. For females, water loss increased rapidly at temperatures above 25 degrees Celsius, figure 4. The intercepts and coefficients of the x, x2, and x3 terms of the polynomial regression equations, table 4, were compared, t-tests, to determine if they differed from each other. The coefficients in the equation for trapped males differed from those for captive females in the x2, p less than 0.05, and x3, p less than 0.025 terms. The intercept and coefficients of the equation for captive males, however, were not different from those for either captive females or trapped males. Although this lack of difference is understandable in the case of trapped males, where the shape of the two curves is similar, concave, it is not so clear for the sigmoid curve of captive females, figure 4. Perhaps the lack of difference in this case is simply due to the small number of observations available for captive males, n equals 10, table 4. Nonetheless, in summer at 35 degrees Celsius, both captive and trapped males relied less on evaporative cooling than did captive females, figure 4. In winter, males and females had similar rates of evaporative water loss across the full range of temperatures tested, figure 5. Therefore, data for both sexes were combined. The intercept and coefficients of this equation, table 4, did not differ from those for summer females, but they did differ from those in the regression for trapped males in the x2, p less than 0.05, and x3, p less than 0.25 terms. As was the case for females in summer, rates of water loss for winter animals increased most rapidly at temperatures above 25 degrees Celsius, figure 5. Figure 4. Relationship between evaporative water loss and chamber air temperatures for raccoons in summer. Captive females, open circles, captive males, closed circles, trapped males, open squares. Lines represent polynomial regressions of evaporative water loss on chamber air temperature. Figure 5. Relationship between evaporative water loss and chamber air temperature for raccoons in winter. Captive females, open circles, captive males, closed circles. Lines represent polynomial regressions of evaporative water loss on chamber air temperature. Table 4. Polynomial regression equations describing evaporative water loss. mg times g to the power of minus 1 times h to the power of minus 1. Of Procyon Lotor in summer and winter, x equals chamber temperature degrees Celsius, y equals evaporative water loss, n equals number of observations, r2 equals coefficient of determination, and SEE equals standard error of estimate. Thermoregulation at low temperatures. Body temperature. Body temperatures in Figure 6 are those recorded during metabolic measurements from animals equipped with surgically implanted, temperature-sensitive radio transmitters. Each point was recorded during the lowest level of oxygen consumption at each air temperature, In both summer and winter, body temperatures were lowest during metabolic measurements at air temperatures around lower critical temperature. At air temperatures below lower critical temperature, body temperatures increased, figure 6, which is an unusual response. Under similar conditions, other proconids either maintain a nearly constant body temperature or allow it to fall slightly. Mueller and Kulzer, 1977, Chevrier-Hugo et al., 1980, Mueller and Rost, 1983, Chevrier, 1985. For our raccoons, confinement in the metabolism chamber at low temperatures must have stimulated a greater than necessary increase in metabolic rate, such that heat production exceeded heat loss, which caused body temperature to become elevated. Figure 6. Relationship between body temperature and chamber air temperature in summer, panel A, and winter, panel B. Captive females, open circles and solid lines. Captive males, solid circles and dashed lines. Solid vertical lines represent lower critical temperatures. Table 5. Regression equations describing oxygen consumption. Milliliters oxygen times g to the power of -1 times h to the power of -1 of Procyon Lotor at temperatures below their lower critical temperature. I equals x-intercept, degrees Celsius, n equals number of observations, R2 equals coefficient of determination, SEE equals standard error of estimate for the y-intercept A, and slope B, x equals chamber temperature, degrees Celsius, and y equals oxygen consumption. And another table I will not read. Summer. During summer, lower critical temperature for male raccoons was 20 degrees Celsius, whereas for females it was 25 degrees Celsius. Figure 2. Regression equations calculated to describe oxygen consumption at air temperatures below lower critical temperature are presented in Table 5. For 3 groups of summer animals, slopes of regressions are identical. This indicates that minimum conductances of these 3 groups were equivalent. Intercepts of these equations are different, which suggests a difference in metabolic cost of thermoregulation between these groups, figure 2. Captive males had a lower intercept than either trapped males, p less than 0.005, or captive females, p less than 0.05, but there was no difference in the intercepts of captive females and trapped males. These regression equations, therefore, also were derived using values of oxygen consumption expressed in terms of metabolic body mass, Mellon, 1963. Relationships between intercepts of these equations are different than those for regressions in Table 5. Intercept for females was indeterminate. Intercept for females was intermediate to, and not different from, those of the 2 groups of males. However, captive males still had a lower intercept than trapped males, p less than 0.025. Thus, in summer, thermoregulatory metabolism was less expensive for captive than for trapped males, and in spite of a 5 degrees Celsius difference in their lower critical temperatures, figure 2, captive males and females had similar thermoregulatory costs. Regression lines for 3 groups of animals in summer extrapolate to 0 metabolism at values equivalent to or greater than normal body temperature. 38.8 degrees Celsius for trapped males, 37.6 degrees Celsius for captive males, and 41.1 degrees Celsius for captive females, Table 5. Thus, all 3 groups had minimized thermal conductance at air temperatures below lower critical temperature. Scholander et al., 1950b, McNabb, 1980b. Minimum wet thermal conductance calculated for raccoons in summer with equation 4, Table 3, is numerically similar to these slope values, Table 5, and it was therefore considered to be the best estimate of minimum wet thermal conductance for Procyon Lotor during that season. 0.0256 milliliters oxygen times g to the power of -1 times h to the power of -1 times degrees Celsius to the power of -1. Winter. During winter, lower temperature During winter, lower critical temperature for both sexes decreased to 11 degrees Celsius, figure 3. Regression equations for thermoregulatory metabolism for males and females in winter are not different from each other in either slope or intercept. These data, therefore, were combined into a single equation, Table 5. Slope and intercept of this equation are both lower, p less than 0.005 and p less than 0.05, respectively, than those for summer animals, Table 5. Identical results were obtained from comparisons using regressions derived from oxygen consumption expressed in terms of metabolic body mass, Mellon, 1963. Thermoregulatory costs at any temperature below 20 degrees Celsius were lower for winter than summer animals, figures 2 and 3. Table 6. Regression equations describing oxygen consumption, milliliters oxygen, G times G to the power of minus 1 times H to the power of minus 1 of Procyon Lotor at temperatures below their lower critical temperature in winter. A equals females with radiotransmitters, B equals females without radiotransmitters, C equals males, I equals x-intercept degrees Celsius, N equals number of observations, R2 equals coefficient of determination, X equals chamber temperature degrees Celsius, and Y equals oxygen consumption. And another table I won't read. Figure 7. Relationship between body temperature and time of day at various months of the year. Captive females, open circles. Captive males, closed circles. Vertical crosshatched areas represent civil twilight. The regression line for Procyon Lotor in winter, Table 5, extrapolates to zero metabolism at 35.2 degrees Celsius, which is below normal body temperature, figures 6 and 7. This suggests that not all raccoons measured in winter minimize thermoregulatory metabolism or conductances at air temperatures below lower critical temperature. Scholander et al., 1950b, McNabb, 1980b. To assess this possibility, data for these animals were divided into 3 groups: A, females with radiotransmitters, B, females without radiotransmitters, and C, males, Table 6. Regression equations of metabolism below lower critical temperature were derived for each group, and based on extrapolated body temperatures at zero metabolism, only the 2 females with implanted radiotransmitters, group A, minimized thermoregulatory metabolism and conductance. Had animals in groups B and C also minimized their thermal conductances while retaining their measured metabolic rates, their rates of heat production would have been disproportionately higher than their rates of heat loss. Equation 4 predicts that under these conditions their body temperatures would have been elevated to 42 degrees Celsius and 40.4 degrees Celsius respectively. Thus, in order to avoid such a large increase in body temperature, animals in groups B and C increase their thermal conductances in preference to lowering their metabolic rates. The regression equation of thermoregulatory metabolism for all winter animals, Table 5, therefore overestimates minimum metabolic cost of temperature regulation below lower critical temperature, and its slope underestimates minimum wet thermal conductance. Consequently, the best estimate for minimum wet thermal conductance for Procyon Lotor in winter is the value calculated for group A animals with equation 4, 0.0172 milliliters oxygen times G to the power of minus 1 times H to the power of minus 1 times C to the power of minus 1, Table 3, and the minimum cost of thermoregulatory metabolism at any air temperature below lower critical temperature is best estimated by substituting this value into equation 4 and solving for HR. Thermal regulation at high temperatures. Body temperature. In both summer and winter, body temperatures increased during metabolic measurements at air temperatures above lower critical temperature, figure 6. This response also was seen during metabolic measurements conducted on other procyonids. Mueller and Kulzer, 1977, Chevalier-Hugo et al., 1980, Mueller and Rost, 1983, Chevalier, 1985. Summer. During summer, our data suggested that the upper critical temperature, TUC, was higher than 35 degrees Celsius. The lowest rates of oxygen consumption at air temperature equals 35 degrees Celsius occurred after 1.5 to 2.5 hours of exposure to that temperature. Prolonged exposure to this temperature in summer did not make animals restless, and their rate of oxygen consumption was very stable throughout each measurement. Body temperature responses at air temperature equals 35 degrees Celsius were recorded from 2 males and 2 females that had implanted radio transmitters. With the exception of 1 male, body temperatures were maintained near 38 degrees Celsius, figure 6. The one exception, a male, maintained its body temperature at 39.3 degrees Celsius. At air temperature 35 degrees Celsius, summer males had rates of evaporative water loss that were lower than those of summer females, figure 4. At this temperature, males dissipated 35% plus or minus 6% and females 56% plus or minus 18% of their metabolic heat via evaporative water loss. Thus, at air temperature 35 degrees Celsius, males must have utilized modes of heat transfer other than evaporative cooling, convective and conductive heat transfer, to a greater extent than females. Winter. Body temperature, evaporative water loss, and metabolic data indicated that in winter, upper critical temperature was very close to 35 degrees Celsius. In winter, the lowest level of oxygen consumption was recorded during the first hour after the chamber had reached air temperature 35 degrees Celsius. Unlike summer, animals became restless after the first hour at 35 degrees Celsius, at which point their oxygen consumption increased and showed a high degree of variability. Body temperature responses at 35 degrees Celsius were recorded from both females that had implanted radio transmitters. In one case, body temperature rose from 37.9 degrees Celsius at the end of the first hour to 40.5 degrees Celsius by the end of the second hour, and as it did not show signs of leveling off, we terminated the experiment. We exposed that same animal to air temperature 35 degrees Celsius one other time during winter. In that instance, its body temperature rose to 40 degrees Celsius during the first 30 minutes and was maintained at that level for 3 hours with no apparent distress. The other female elevated its body temperature from 37.3 degrees Celsius to 39 degrees Celsius during the second hour at air temperature 35 degrees Celsius and maintained its body temperature at that level for 2 hours. Thus, during winter, prolonged exposure to air temperature 35 degrees Celsius stimulated more of an increase in body temperature than it did in summer. During winter, both males and females increased evaporative water loss at air temperature 35 degrees Celsius, figure 5, but only to the extent that they dissipated 35% plus or minus 10% of their metabolic heat production. Thus, even in winter, convective and conductive heat transfers were still the most important modes of heat loss at this temperature. Daily cycle of body temperature. The daily cycle of raccoon body temperatures during summer and winter are presented in figure 7. In general, body temperatures showed a marked circadian cycle in phase with photoperiod. Body temperatures rose above 38 degrees Celsius for several hours each night, but remained below 38 degrees Celsius during daytime. During summer, with the exception of one female whose record was not typical, figure 7, body temperatures rose above 38 degrees Celsius shortly after sunset, whereas in winter, body temperatures did not rise above 38 degrees Celsius until several hours after sunset. Once body temperature was elevated, it usually remained so until just before or after sunrise, figure 7. During summer, body temperature was above 38 degrees Celsius for 85% or more of the time between sunset and sunrise, 87% for the female with the typical body temperature pattern, and 85% and 98% for males. Whereas in winter, it was elevated for only 47 to 78% of the time between sunset and sunrise, 47% and 61% for females, and 67% and 78% for males. During night, body temperature would oscillate between 38 degrees Celsius and about 39 degrees Celsius, such that 2 peak values occurred. These peak values presumably corresponded to 2 periods of heightened nighttime activity. During summer, one of these peaks occurred before and the other after 2400 hours, whereas in winter both peaks occurred after 2400 hours. With the exception of one female in winter, figure 7, the lowest body temperature of the day for both sexes was 37 degrees Celsius, and this typically occurred during daytime, figure 7.